This example we're looking at an inverted cone and it's being filled with water. So you can see there's a little bit of water in there already. So you can imagine there's water going into this cone and the water is going in. It says here water is flowing from a tap at a rate of K litres per minute. So actually I might just do this in red so you can see. So we've got K litres per minute going into that cone. You can see here that it says an inverted cone has a height of h centimetres, and that's been shown here. Now the height of the cone will not change, so that's a constant. It has a radius of r centimetres, so you can see here they've shown that it's 2r across, but really if you want to, you could show the radius of the cone is r across. And again, just like with the h, this is a constant. It will not change because the cone's not changing its shape. The depth of water in the cone is x centimetres. Now this is a variable, and that's because the water can go up or down. And in our case, we're only putting water in, so it's only going to go up, but it will increase. So it's not going to stay the same. And we've also got time t as minutes. So we've got time equals t. We've got the depth of water equals x, and that's in centimetres. And we've got the height of the cone in centimetres as well, and radius in centimetres. Now it asks us to construct an appropriate differential equation for dx dt. What that means is that we need dx dt. But because this is going to be looking at rates and related rates, we have to look in the question, do we know any? Now we know, we've written it down already here, that we've got litres per minute. So this would be a change in volume with respect to a change in time. Now we could be looking here at volume in terms of litres, but because everything else here is in centimetres, it probably makes sense to make your volume in centimetres cubed, so that you've then got height and depth in centimetres, time in t, and volume in centimetres cubed. Now there are 1,000 cubic centimetres in 1 litre. So that means here for our dv dt, it equals k litres per minute, which is the same as k times 1,000 centimetres cubed per minute. So we're going to use dv dt equals, oops, I'll write it the other way, 1,000k. Okay, because we're looking, everything in centimetres cubed makes more sense. It's a volume in centimetres cubed because everything else is in centimetres. So we've got dv dt. Now we need dx dt. So the problem here is, do we have a relationship between, we've got the dt here, so that's cool. We need some kind of relationship between x and v. So we can end up with a dv dx, and that will help us to eliminate this dv. So what we'd need is a relationship between v and x. Well, that would be something that links to our volume here. So we're looking here at the volume of what's in that tank. So the volume is going to be the volume of the cone with height equal to x, because this is the section that's changing. We also need to give our cone here a different radius as well. We can't use radius r because it's been used already. So we'd be looking at a cone, we'll call this y, and we'll call this, we know this is x. This is the water. So this is the volume of water. So volume of the cone with height equals x, and let's say radius equals y. You could use whatever you want. I'm just using x and y. Okay, so what I'm going to do is now use, I'll just make all this black so we can see it, use our formula sheet, because we know that we're looking for volume of a cone. Okay, so if I go into my formula sheets, you can see here we've got volume of a cone is 1/3 pi r squared h. Now in our case, h is going to be, I might copy this over actually so we can see it, h is x, and r, our radius, is y. So if we use that formula, we're going to have our volume equals 1/3 pi, r squared is y squared, and h is the height, which is x. Awesome. So we've got a relationship now between v and x. The problem with this relationship, however, which is a bit sad, is that you've also got another variable in there, and that variable is y. and we really don't want y, because y is a variable because it changes. So a variable, this is also a variable. So what we want to try and do here is just get all constants in here with the x. And in order to do that, we're going to need to look at the relationship between the volume of the water in the cone and the actual volume of the entire cone. All right, so I'm just going to draw here a couple of triangles on the cone so that you can see. We've got a triangle formed with a height of h and a length here of r. So I'll do it inside the cone. So that's our cone height, and across is r. Okay. We also have another triangle inside this cone, which is the triangle here formed from the water. That triangle, I'll do this in yellow, has y as its side length and x as its height. So you've effectively got two triangles here, and the cool thing about these triangles is that these are similar triangles. So if we have a look, this is a representation of what's going on. We've got our big triangle and our little triangle. These are actually both similar triangles. And when we're dealing with similar triangles, they're in ratio that's in proportion to one another. So if we think about the big triangle, we've got the height is to r, so the side length r, as x is to y in the smaller triangle. So that's your big triangle, this is your small triangle. Now when you're working with ratios, what you can do is you can cross multiply these ratios. So you end up with h times y equals r times x, and that can allow you to solve for one of those particular variables. So we're going to solve this for y. So y equals r times x over h. And that's cool because that means we can now eliminate y from our previous volume equation. So I'm just going to take this, bring all this over onto the next page. So we've got our volume. Now what we're going to do, I can actually still use that same arrow, is we're going to substitute y into here, so into y squared. So we now have, now we've got v equals 1/3 pi of y squared, where y is rx on h, that's all squared, times x. So that's going to be pi on 3 r squared x squared on h squared times x, and that means that v will be given by pi, I'll just put everything like on the top and the bottom here, so we've got pi r squared, this will become x cubed over 3h squared. So that's our relationship between v and x, which is going to help us out with finding dx dt. Now the thing that's really important to note here is that all of the stuff there that I've circled in green is a constant. So effectively this is just v equals a times x cubed, where a is a constant. So when we differentiate this, which we're going to do now, this just stays the same. So remember that we need dx dt, we have dv dt. We needed a relationship between v and x so that we could get a dv dx and then help us to get dx dt. So now, do this in red, let's differentiate both sides of that equation. So we get dv dx equals, the derivative here will be 3, so the power coming out the front, 3 pi r squared x squared on 3h squared. So that means that we now have dv dx equals, 3's will cancel, pi r squared x squared on h squared. We also know dv dt was 1000k. dv dt equals 1000k. Now, using related rates, we can find what we needed all along, which was dx dt. So I'm just going to write here, using related rates, we've got dx dt, which is what we want, would be equal to dv dt, because that has the dt on the bottom, times, now we need the dx on the top. Here you can see the dx is underneath. So we're going to have to flip this over, so we get dx on the top and dv underneath. So we have dv dt is 1000k times dx dv, which is dv dx flipped over. So we have that. So that means that we now have dx dt equals 1000 kh squared over pi r squared x squared. And I'll do a big box around that. because that is our differential equation. Let's go back and read the question again, see how we're going. The inverted cone has a height of h, we've used that in our similar triangles, a radius of r, we've also used that. Filled with water flowing from a tap k litres per minute, that was dV dt, which we converted to centimetres cubed. The depth is x centimetres of water at time t, so we've put that into our equations. We need to construct an appropriate differential equation dx dt. We've done that, that's awesome. We now need to solve it, and that's given that initially the cone was empty. Now what I've just written under here is what that means. Initially refers to when the time is 0. So initially when the time is 0, there is no water in this tank, so the water is non-existent, which means the height of the water, x, will be 0. So initially the cone is empty, means that we have an initial condition when t equals 0, x equals 0, and that will help us to solve dx dt. So our job now is to solve dx dt where t equals 0, x equals 0. So I'm going to pick up this differential equation now, take it onto the next page so we can solve it. I'm going to solve this by separating it out. So I'm going to separate and integrate. So I'm going to take the dt up to this side, and all the x stuff, all of this is just a constant, so the x is just the x squared, the x component here. I'm going to take that to the other side as well, and bring this up. So we're going to have x squared dx equals 1000 kh squared 1 pi r squared, and bring the dt up. I'm now going to integrate both sides. So we have integral, all we have to do is simply add an integral sign to each side, because we've already got the dx and the dt that we need. Integrating, we get x cubed on 3, which equals 1000 kh squared 1 pi r squared. Remember, this is all a constant, and because we're integrating with respect to t, this will become the coefficient of t plus some other constant. I'm now just going to rearrange this so I get x cubed on its own, bring the 3 up, so we'll have a 3000 on the top over pi r squared, plus, I'm just going to relabel this as m, and the reason I've done that is I've just said that m equals 3 times c. Just makes it a bit neater so I don't have a 3c there, that's all. And I'll do this in red, put a box around that. So we're nearly finished with this one. Alright, now using our condition, when x equals 0, t equals 0, that implies that x cubed, which is 0 cubed, equals t times all of this, which is 0, plus m. So that means that m is actually equal to 0. So we then have our solution, x cubed equals 3000 kh squared t over pi r squared. And remember that we were solving dx dt. Always look up at what variable is on the top line. That's what we're going to solve with respect to. So we're now going to solve for x. And doing that, we're going to take the cubed to the other side, where it becomes a cube root. So we'll have the cube root of 3000 kh squared t over pi r squared. And this is our particular solution. It's a particular solution. Just rewrite that. Particular. It's a particular solution because we had an initial condition, which was x equals 0, t equals 0, that we had to put into our differential equation. So going back to the question, just making sure we've solved it. Find dx dt, we did that, and solve it, given that initially the cone was empty. So t equals 0 and x equals 0. So that's our solution there to the differential equation.